In this recording, we discuss the concept of resistance. As was mentioned earlier, resistors dissipate energy as power, where the power is the voltage across the resistor times I. And again, resistance, the definition of resistance is how difficult it is for charges to get through the circuit, that particular element in the circuit. And the voltage drop across that element is related to the resistance through this expression. One thing I would like to point out before going on, when we set up a battery in a circuit, the effect of the battery is to exert a force on the charges in every element in the circuit. So this is a graphic representing that. This is the electrical field due to the battery. So associated with that electrical field, there will be, of course, the electrical force. Now, look here what we have in this circuit. We have electrons. All of these electrons are going to be subject to an electrical force that's going to be opposite in direction to the electrical field. Remember, F is equal to QE. Now, as they move, they are going to navigate around ions, the rest of the atom, essentially electrons and the positive nucleus, and they are going to navigate around other electrons. Now, for an electron to move from here to here, it does not have necessarily a straight path. It's going to be a path that's affected by other electrons, by the other charges available within the material, and it's going to depend on how is that material configured, how close are the atoms to each other, are there imperfections in the material, and so on. Now, a good way to explain how resistance affects charge flow is by using a highway example. Now, in the highway example, we are going to think of the highway as the resistor, as the element that's going to provide resistance, and our electrons are going to be the cars in the highway. These are going to be our charges. Remember what current is. Current is charge per unit time. The amount of charge per unit time. Now, what's going to affect the charge flow or the car flow in a highway? I grabbed two pictures here from online. Okay, in both pictures, you notice here it's just a two-lane highway, but essentially cars can move only in one lane. Now, you notice if I have a slow car, that slow car is going to result on all the cars behind it being slowed down. And we see that here and we see that here. What does that mean? Slow car, meaning when we talk of current, is I is Q over T, slow increase in the time, making the current smaller. So one of the things that's going to affect the current is the inability of cars to move faster. And that inability can be due to the fact that they are restricted to a one-lane road in this case. If we have a wider road like this one, even if we have some slower vehicles can navigate around and get in faster. So the overall speed of charges in the highway is going to be faster. In this highway, it's going to be faster than here. So faster speed, meaning more current, meaning the charges have experienced less resistance for the same length of highway. So if we have the same length of highway, if we have one lane, it's going to be a higher resistance than when we have multiple lanes. Now, of course, the length of the highway itself is going to result in more resistance. the more highway, the more difficult it's going to be for the cars to navigate. The longer it is, the more difficult it is, and the more energy they are going to lose. Now, what else is going to affect resistance? The highway itself. You can have speed bumps like here. That's going to slow down the current. You can have construction like here and speed bumps. Think of the other vehicles. Think of potholes. All of these imperfections in the highway, think of their equivalent in an electrical circuit. All of these contribute to resistance. The more cars on the highway, the more difficult it's going to be for you to navigate. Slower cars or slower highway users are going to make it difficult for the cars to travel on that highway, meaning the current is going to be less. So, electrically or mathematically, what's going to affect resistance? If we take this blue material and look at it as a cylinder, and this here is the cross-sectional area of the cylinder, and this is the length of the cylinder. Okay, we have it represented here. Now, think of that as your highway. The bigger the cross-sectional area, the more lanes you have. The bigger the cross-sectional area, the less is the resistance and the easier is it for it's going to be for the chargers to move. So that's going to affect resistance in the denominator. Okay, let me write it here. So resistance is going to be inversely proportional to the area. The longer the wire is, the more potholes it's going to, the chargers are going to meet, the more speed bumps, the more other chargers they are going to meet, so the more resistance they are going to experience. So the resistance is going to be proportional to the length. The longer the length, the more resistance. And then the actual configuration of the material is going to affect the resistance, and that's through what we call resistivity. So resistance is given by rho, the resistivity, times L, the length of the wire, over A, the cross-sectional area of the wire. Okay. These are the parameters that affect resistance. Now, for a perfect resistor, the current is given, for a perfect resistor, the resistance is constant and the current is given by V over R, which means you double the voltage, you get double the current. Not all elements have perfect resistance. Resistors are as close to that as it can be. So resistors obey what we call Ohm's law. Okay, this is what Ohm's law says. V is equal to IR. The bigger the resistance, the less the current, and vice versa. The unit that we use for resistance, I should have mentioned it in the previous slide, but it is ohms. We call it ohms, and the symbol we use for it is omega. The unit for current is amps, the unit for voltage is volts. Let's see. How much voltage is being supplied to a circuit that contains a 1 ohm resistance if the current that flows is 1.5 amps? Okay. So they give us the resistance R, they give us the current, and they're asking us for the voltage. V is equal to IR, so we just multiply them. 1.5 amps times 1 ohm, so it is 1.5 volts. Then we have this other example, a 12-volt battery is powering headlights that draw 2 amps of current. What is the effective resistance in the circuit? So in this case, the relationship is again V is equal to IR, but we know V and we know I. And we are asked to solve for R. So R is equal, I divide both sides by I, so it's V over I. So in this case, that's going to be 12 volts over 2 amps. So 12 over 2, that's going to be 6 ohms. In a circuit, when we add batteries, what's the effect of adding batteries? Now, if we place them end to end like this, this is what we are talking about, is connecting them with a wire like this and with a wire like this. And then connect them to our resistor or light bulb or whatever. What's the effect on the circuit? Now the thing is, each battery results in a voltage difference. However, I have a wire connecting both of them. A wire connecting this positive end of the battery to this other positive end of the battery. So which means, remember what we said about wires, the electrical potential here through here is the same. If it is a 1.5 volt battery, now throughout these wires, the blue one is 1.5 volts. Now the bottom, and the negative lead, that's going to be the same electrical potential as well. So if it is a 1.5 volt battery, that's going to be 0 volts. So what does this mean? It means that the battery is not going to increase the voltage if we add it in this type of configuration to the other battery. This kind of configuration, we call it parallel. They are both parallel to each other. Both their positive ends touch and their negative ends touch. Now, when we add batteries in parallel, they don't affect the voltage we provide to the circuit. Actually, let's go to the simulation. Now, this is my light bulb. What I'm going to do is add another battery. And to add it in parallel, I'm going to place the light. Oops. I didn't mean for that to happen. Okay. Now, so I'm going to try to put it in parallel with the other battery. To do that, I'm going to take a wire and connect the positive lead of one to the positive lead of the other one, and the negative lead of one to the negative lead of the other one, and then connect the circuit to the rest. And notice here, the light did not change. Okay, I disconnect one battery, and you should see the same amount of light. Put it back, same amount of light. Voltage, I have 9 volts here. I disconnect one battery, it's still 9 volts. So the battery, adding a battery in parallel, did not affect the operation of the circuit at all. One might ask, why would we do that then? Why would we put batteries in parallel? Okay, you put batteries in parallel to make your light bulb light up for a long time. What you are doing when you are putting it in parallel, you are using more energy. You are converting more of the chemical energy here in the batteries into electrical energy. Now, a battery is made out of chemicals. The more of them, the more chemicals we have. That's why, for example, smaller batteries are going to last less than larger batteries because they have less chemicals. Now, what about if we place the batteries in series instead, one on top of the other, and connect the positive lead of one of them to the circuit and the negative lead of the other one to the circuit? The story then is different. So the first battery is going to result in a change in electrical potential of 1.5 volts. From here to here, 1.5 volts. However, the second battery is going to also result in a change of 1.5 volts. So from here to here, we are going to have a change of 1.5 volts, meaning I go from 1.5 to 3 volts. So overall to the circuit, from the negative end of the first battery to the positive end of the second battery, I have an electrical potential difference of 3 volts. So when we connect the batteries in series, we are going to have an added voltage. And let's go to the circuit. I'm going to disconnect this one here. Okay, now so I'm going to connect a wire here. I did not really have to have the wire, but I'm doing it so we can easily measure the voltage. But when I do this, you see we have more light. And actually look at the voltage that we have between the wires. It is 18 volts. Between the first battery, across the first battery, it's 9 volts. Across the second battery, it is 9 volts. But then the first battery results in a 9 volt increase in electrical potential. The second one, an additional 9 volts, giving us 18 volts here. Now, just a reminder, remember wires in a circuit ideally have zero resistance. Remember, wires in a circuit, conductors in a circuit, are idealized as zero resistance, meaning that the voltage across them is zero. The electrical potential across them is zero. So actually, whenever you have wires in a circuit, you can use a coloring pen, for example. You can assign a voltage for each segment, and the voltage is going to be the same throughout. For example, in this circuit here, all the green is 1.5 volt, all the blue is 3 volts, all the brown is 1 volt, all the orangish is 0 volts. Each segment is going to be at the same electrical potential.